All right, calculus, we're in chapter 6 now, and we're not going to go 6.1 through 6.3, just 6.1 through 6.2. And we're considering really the application of the integral, and we've talked a lot about area bounded beneath the curve. The question is this right now is, what about if we have the function f of x, and then we have a different function, we'll say g of x, and you're going to bound those from a to b. And you want to know the area between those two curves. And it might seem, kind of a challenging question to ask, but again, this is what we're looking for. We're looking for that exact area. And it's a weird shape, but finding the area is not that bad. And this is going to kind of be interesting to you as we calculate this. We would say that this is important. You might want to say draw a rectangle. So we could find the area of one rectangle. If we want to find the area of one rectangle, we actually say that the width of this is dx. dx. dx refers to the width. So that's why you're always seeing at the end of an integral there. And here's the time where I bring it up. So what about the height? Well, it's not too tough to figure out. Suppose that this had a height of 8 and this had a height of 5. You would say that the height of the rectangle would be 3 because the difference between the two is 3. So in fact, that height right there is f of x minus g of x. So the area of one rectangle is simply going to be f of x minus g of x dx. But we don't want the area of one rectangle. We want the area of an infinite number of rectangles. And so we could go from 1 to infinity rather quickly by simply just slapping on an integral, and that's what it does. And that's the beauty of it. Bound it from a to b, done. So subtract the top function minus the bottom function, and away we go. Let's check out a couple examples here. We got y is equal to x squared minus 2x plus 3 over the interval 0 to 1. So always good to get a graph sketch. Now I think in your assignments, I've really tried to put together the sketches of the graphs for you. I'm going to graph negative 2x plus 3. So 1, 2, 3 over 1, 2, 3, so on and so forth. So I'm going to plot 3. I'm going to go down 2 and over 1. And so you can see I get that shape right there. So that's one function. And then you have another function, which is x squared. That's going to look like that. And what we want to know is we want to know the area between those two functions from 0 to 1. So you're going to look at this area right there between 0 and 1, it says. And so you can see from that picture that the top function is going to be negative 2x plus 3, and that the bottom function is x squared. Therefore, and this is important as well, if you were to draw that rectangle for the top and the bottom, you would say that that rectangle, it has what we would say is horizontal width. So it has width going sideways, so we call it dx. We'll get more into that later, but so top, bottom. So we take the top function, negative 2x plus 3, and we subtract the bottom function, dx. So this is my height, this is my width, and we integrate 0 to 1. And now we just determine that. The antiderivative of negative 2x is negative x squared. The antiderivative of 3 is 3x, and the antiderivative of negative x squared is negative x cubed over 3. And it's a definite integral, so we put the 1 in the 0. Plug in the 1, and we get negative 1 plus 3 minus 1/3. Minus, if you plug in 0, you get 0. So you can see we have 2 minus 1/3, or 6/3 minus 1/3 is in fact 5/3. And that's the work that you show. So pretty cool problem. Let's try a few more. Find the area bounded between these two curves. They don't give us any bounds. Well, let's sketch the graph and figure out the bounds. X squared minus 2x plus 1. I know that factors to x minus 1 times x minus 1. So therefore, I know that it's centered right at 1. It looks like that. And then 2x plus 1, see, it's going to go through 1, and it's got a slope of 2. So it's going to look something like that. So it's going to cross way up there. So we'll try to bring those together. So I'm looking for this. And again, if I draw the rectangle, you can see what the top function is. It's the line. And then the parabola is the bottom function. So this has what we call horizontal width. So the width is dx. And that's important. Horizontal width dx. Vertical rectangle, but horizontal width. So we got our top function. 2x plus 1 minus our bottom function, x squared minus 2x plus 1 dx. As we subtract those, you can see that you have the integral of negative x squared. 2x minus negative 2x is positive 4x. And then 1 minus 1 is 0. So it becomes that. But we have our bounds. Well, we don't really know our bounds till we find the intersection. And the way we find the intersection between these two functions is we can simply set them equal to each other, and that will determine the intersection points. Notice that if we subtract the 1, the 1's go away. And notice if we subtract the 2x over, we get x squared minus 4x is equal to 0. Factor out the x, and it looks like the intersection point is at 0, which we knew, and then the other one up here is going to be at an x value of 4. So we bound this from 0 to 4. The antiderivative of negative x squared is negative x cubed over 3. The antiderivative of 4x is 2x squared. We're going to evaluate it at 4 and at 0. If we plug in 0, we get 0. If you plug in 4, you get negative 64 over 3 plus 16 times 2 is 32. Or negative 64 over 3 plus 96 over 3, and that's 32 thirds. Really nice problem right there. Let's try a couple more. Find the area bounded between the curves sine of x and cosine of x over the interval 0 to pi over 4. Fortunately, you know what the graphs of sine of x and cosine of x look like. If I divide this up 2 pi, this would be pi, 3 pi over 2, and then we have pi over 2. The graph of sine of x, if I go up to 1, it starts here and it goes up, back down, to the bottom, back up. So I hope that you understand what the graph of sine of x looks like. And then cosine of x is, it's going to start up here. And it does that guy, okay? So that's what we got. Now we want to bound it from 0 to pi over 4. And so it just turns out that that spot right there is in fact pi over 4. So we want to find that area. Again, as you draw the rectangle from top to bottom like that, you can see again that it has what we call horizontal width, dx. We'll get to a non-horizontal width here in a little bit. But let's just set it up. The integral, the top function you can see is cosine of x. Minus the bottom function is sine of x, and you're going to integrate 0 to pi over 4. dx. Antiderivative of cosine is sine. Antiderivative of negative sine is positive cosine. Now, everybody out there, you know that, we got 2 spots here. We got that, and we got 0, 0. It has a terminal point of 1, 0. And that is a terminal point of root of 2 over 2, root of 2 over 2. So the sine of pi over 4 is the root of 2 over 2. Plus the cosine of pi over 4 is the root of 2 over 2. Minus the sine of 0 is 0. Cosine of 0 is 1. So add these together, we get the root of 2. We get the root of 2 minus 1. That's your result. Let's check this guy out, see just a little bit different. I'm going to show you a little bit of a trick here. And after that, I think we just got one more. Yep, we'll do one more, and we'll call it a day. So you guys are doing well. We're at 10 minutes. We'll probably go to about 20 here. These last two, well, maybe it's faster. X to the fourth looks a lot like x squared. It's just wider, so it looks, maybe something like that. And then 2x squared minus 1, it's a parabola that's shifted down 1. And it comes up and it just touches tangent on the sides. So what we're looking for is this area right here. And so you can see the top function is definitely x to the fourth, and the bottom function is 2x squared minus 1. But we got to figure out these intersection points. And the way we figure out those intersection points, we set them equal to each other. X to the fourth equals 2x squared minus 1. Or x to the fourth minus 2x squared plus 1 is equal to 0. And that factors to x squared minus 1 times x squared minus 1. Or x plus 1 times x minus 1 times x plus 1 times x minus 1. Notice there's double roots, so negative 1 and negative 1, positive 1 and positive 1. It's a good indication that it touches tangent both at positive 1 and at negative 1. The other thing that you would hopefully notice is that both of these functions are what we call even functions, which means that they're symmetrical about the y-axis. So whatever you have on that side is the same that you have on that side. And so I'm going to show you a little trick here that's really cool that happens in those situations. First of all, you have the integral of the top, which is x to the fourth, minus the bottom, which will give me a negative 2x squared. When I distribute the negative, it will give me a plus 1 dx. And we're going to integrate from negative 1 to 1. Now, I don't know about you guys, but I really like when this bottom number here is not negative 1. I like it when it's 0. And so in this situation, because the functions are what we call even functions, they're symmetrical about the y-axis, you can, in fact, do this. We're going to do the integral from 0 to 1 of x to the fourth minus 2x squared plus 1 dx. And we're simply just going to double it. You can see that it's the same on both sides. The area will be the same. And so now we just go ahead and we find the antiderivative will be 2 times x to the fifth over 5 minus 2x cubed over 3 plus x. And you're going to evaluate that at 1 and at 0. So we get 2 times 1/5 minus 2/3 plus 1. Well, so if you plug in 0, you get 0. In this situation, if you find common denominators, we'll have 2 times, let's see, it'll be 3/15 minus, let's see, that'll be 10/15. That'll be plus 15/15. So 3 minus 10 is negative 7. Negative 7 plus 15 is 8. So 2 times 8/15, which is 16/15. And that's that exact area bounded between those two functions. It's super cool problems. Now we get to our last one. Y equals 2x minus 2 and x equals y squared minus y. So what's important to notice about this is it's a parabola, but it's a sideways parabola because it's x equals. Now, some of you maybe remember we covered this during our distance learning last year in March. If you don't remember, it's not that big of a deal. Just know that if it's x equals, it's horizontal. Instead of going through the x-axis, it goes through the y-axis at 0 and 1. So I could sketch a pretty basic graph of that by simply going like this. I'm going to go through 0, and I'm going to go through 1. Okay, and so I'm going to go through those 2 points. Graph is going to look something like that. And then the other one, it's down 2, so down 2. And then I rise 2 and I run 1. So there, and rise 2, run 1, so like there. Okay. So this is a super important example. And it's so important that you follow what's going on here. Notice if you look at the top function, you would say, well, the top function is the parabola and the bottom function is the line. But if you draw the rectangle over here, then you can see that the top function is the parabola and the bottom function is the parabola. And if you end up with the, if you end up with a parabola, minus a parabola, you're going to get 0. They both just go away. So you can't have a situation where the top is the same as the bottom. And that's why drawing a rectangle that's vertical does not work. Instead of drawing a vertical rectangle, we draw a horizontal rectangle. And you can see anytime you draw a horizontal rectangle, the right side is always going to be the line, and the left side will always be the parabola. The right side is the line, and the left side is the parabola. So instead of doing top minus bottom, we are going to do right minus left. So it's right minus left. Okay? Look at the thickness of your rectangle. Instead of having vertical thickness, or instead of having horizontal thickness, it has vertical thickness. The thickness is up and down. So it is dy. That's extremely important. Integral, thickness is dy. We do not top minus bottom, but right minus left. So the right is the 2x minus 2, and the left is the y squared minus y. Now this is problematic because as you notice, I have two different variables. Can you guess whether or not I want to write this in terms of y or in terms of x? Sure enough, dy tells me that I need to write it in terms of y. Here I have an x. I have to get rid of that. So let's write it so that it's an x equals instead of a y equals. Y plus 2 is equal to 2x, and divide by 2 and we get 1/2 y plus 1 is equal to x. Great. Now I can rewrite this integral to be 1/2 y plus 1 minus y squared minus y dy. Finally, it's important for us to be able to determine the points of intersection. Instead of the intersection being x values, it needs to be y values. Now, we are trying to find these y values because we would draw our rectangles, this way. So instead of being an A and B side to side, it's an A and B for top to bottom. We go all the way up to, all the way up to there and all the way down to here. So we want to find those red dots, the top and bottom, instead of the left and the right. Well, how do we do that? Well, it's not too bad. You have some options here. In fact, we know that x is equal to this guy. So I'm just going to take this and dump it in for x. And so I have y is equal to 2 times y squared minus y minus 2. Or y equals 2y squared minus 2y minus 2. If I subtract the y, I get 0 equals 2y squared minus 3y minus 2. And that factors to 2y and y minus 2 and a plus 1. Notice I have a solution of 2 and negative 1/2. Look back at your graph. Does this look like it's a height of 2? Sure does. And does this look like a height of negative 1/2? It sure does. Folks, I think I've done most of the work for you in terms of finding the intersection. There's very few problems where you have to do. I've tried to include in your worksheets plenty of graphs that tell you pretty well where you need to look. But now we can go ahead and we can determine this integral. It's been a fair amount of work, but you should be ready and capable of doing a problem like this. So, negative 1/2 to 2. Looks like I have a negative y squared. 1/2 y minus negative y is going to be a positive 3/2 y. And it's a plus 1 dy. And we integrate. The antiderivative of negative y squared is negative y cubed over 3. The antiderivative of 3 over 2y is y squared. And then it'll be a 3 over 4 plus y. Have some arithmetic here to do. Plug in the 2 and we get negative 8/3. Plug in the 2, we get 2 squared is 4. Divide by 4 is 1 times 3 is 3. So that'll work out nice. Plug in the 2, we get 2. Plug in negative 1/2. Negative 1/2 to the third is negative 1/8. Negative makes it positive 1/8. Divide by 3 is 1/24. Plug it in here, 1/2 squared is a 4th. Divide by 4 is a 16th, so we get 3/16. And then we get minus 1/2. All right, let's just find a common denominator. Everything multiplies to, let's see, I'm going to 48 on this one, 48. So I'll multiply top and bottom by what, 16? So 8 times 16, it's going to be 128. Negative 128 over 3 plus 48 over 3 plus, whoop, sorry. So we're going 48 on the bottom. So now 3 times 48 is going to be 144. 96 over 3 minus, let's see, that's going to be 2 over 48. Distribute the negative, minus 9 over 48. And it'll be a plus, it'll be 24 over 48. So we just simply add up those together. Negative 128 plus 144 plus 96 minus 2 minus 9 plus 24. I get 125 over 48. There you go. Tough problem there, but just notice that in some of your situations, you're going to have to draw horizontal rectangles and not vertical rectangles. So I'm going to quick make sure that you understand, so we're at 22 minutes. Quick make sure that you understand your worksheet here. As I pull out your worksheet, area between two curves, I just want you to know for problem 1, definitely have vertical rectangles. Number 2, vertical rectangles. But number 3 and 4, those are horizontal rectangles, So just note what you're drawing. But don't be surprised if you could get confused with a problem or two. This isn't easy stuff. We'll be ready to talk about it in class. Have a good day, folks. We'll talk to you later.